As for the blade, the outer skin is fiberglass. There's a stainless steel erosion strip at the front. It's got a fiberglass spar at its leading edge for added strength, called a D-spar because of its profile shape. The core is Nomex honeycomb material. Nomex is a proprietary fibrous material that's strong, light, and can withstand lots of heat. The trailing edge is also a fiberglass strip, with a trim tab at its midsection to balance individual blades. The blade droops while resting, but lengthens and becomes strong with centrifugal forces during flight. The blades and their connecting parts form a much more organic system than it first appears. It's flexible yet very strong, self-adjusting to elegantly meet complex flight conditions. Let's follow the chain of components down to see how pitch changes are handled. All of the parts you see here make it possible to enact both collective and cyclic pitch change to the blades while the rotor is spinning in flight. Each blade has a pitch horn, as we saw previously. Pitch link tubes extend downward with spherical bearings at the end that allow some movement. They connect at four sides to the swash plate assembly. This contraption is what translates input from relatively stationary components to rotating parts. You can already see that, as the swash plate tilts, each pitch link gets specific, individual input. The swash plate assembly has two main parts. The lower plate, which doesn't rotate, rides on a large spherical ball called the pivot bearing that allows it to tilt in all directions. It has a hinged bracket or scissor link to stop it from rotating vertically. The lower plate holds large bearings upon which the upper plate smoothly rides, allowing it to spin as it rests on the lower plate.